In this video, we will be proving the triangle inequality. The triangle inequality states that the modulus of a plus b, where a and b can be two complex numbers, is always less than or equal to the modulus of a plus the modulus of b. And notice that I didn't say the absolute value of a and b, because what's the difference between the absolute value and the modulus? Well, the modulus is actually the generalization of the absolute value, but for complex numbers. Remember that real numbers are contained within the complex numbers. And so taking the modulus of two real numbers is the same thing as taking the absolute value. However, when it comes to complex numbers, remember that complex numbers can have an imaginary part. Essentially, the modulus is the complex counterpart of the absolute value. So a and b are complex numbers, which means that, for example, a can be written in the form x plus iy, where x is a real number, and it's called the real part of a. So x is the real part of a, and y is also a real number, and it's called the imaginary part of a. Furthermore, I is the imaginary number, and one thing to note is that the modulus of a is the square root of the real part of a squared plus the imaginary part of a squared. And therefore, the square of the modulus of a is the square of the real part plus the square of the imaginary part. And I just want to reiterate one final thing. Since the triangle inequality works for complex numbers, it also works for real numbers. And so if a and b are real, this inequality holds. Now, the way we will go about proving the triangle inequality is we will first assume that the inequality is true. And then we will do some manipulations in order to obtain a result that we know for a fact is always true. And since the triangle inequality will be equivalent to something that is always true, this means that the triangle inequality is also true, because we have worked in terms of equivalence. So we start from the triangle inequality, and obviously it's kind of hard to work with this, and so what we will do is take the square on both sides. And the reason we can take the square on both sides is because the modulus of a plus b is always a positive number, and the modulus of a plus the modulus of b is also a positive number. And therefore, we can say that the triangle inequality is equivalent to a plus b, the modulus of a plus b squared, which is less than the modulus of a plus the modulus of b, everything squared. And so remember that the reason we can take the square on both sides is because this expression is positive and this expression is positive, which means that it is equivalent to taking the square on both sides. And this inequality holds even when we take the square, because for strictly positive numbers, the square function is a monotonically increasing function, which preserves the inequality. And so now we can distribute. So we have that the modulus of a plus b, everything squared, is less than or equal to the modulus of a squared plus 2 times the modulus of a times the modulus of b plus the modulus of b squared. Now, one property that is extremely useful when it comes to taking the modulus of a complex number is that the modulus squared of any complex number, for example a, is equal to that complex number multiplied by its conjugate. So this is the notation for the conjugate of a complex number. Note that we can also write the complex number as being a star, but it's just a matter of notation. Now, why is this property useful? Well, thanks to this property, we can rewrite this expression. Indeed, the modulus of a plus b squared is a plus b, multiplied by the conjugate, which is a plus b, and the modulus of a squared is also a times its conjugate plus 2ab plus b times its conjugate. Now, another property that we have is that when we add two complex numbers and we take the conjugate of that, well, it's the same thing as taking the conjugate of the first number and add it with the conjugate of the second number. So by virtue of this property, we have that this is equivalent to a plus b multiplied by the conjugate of a plus the conjugate of b is less than this whole expression right here. And now if we distribute this expression, we have that a times its conjugate, a, plus b times its conjugate, plus a times the conjugate of b, plus a conjugate times b is less than the expression on the right. And what's neat about this expression is that we can simplify a lot of terms. For example, a times its conjugate can be cancelled out on the other side as well, and similar for b times its conjugate. And so we get this expression over here. Now, what's great about the expression on the left-hand side is that the two terms are actually conjugates of each other. And to see this, we can show that the conjugate of the product of a times the conjugate of b is actually the conjugate of a times the conjugate of the conjugate of b. But the conjugate of the conjugate of b is just b itself. So we have the conjugate of a times b. And so this means that the conjugate of this product is equal to the conjugate of a times b, which means that this expression over here is the same as a times the conjugate of b plus the conjugate of this product, so a times the conjugate of b. And an interesting property when it comes to complex numbers is that when we add two terms that are complex conjugates of each other, well, we get twice the imaginary number of the complex number. And so this expression plus its conjugate is equal to twice the real part of the complex number, so a times the complex conjugate of b. So let me reiterate what we have just shown. We have seen that the product of the conjugate of a times b is actually a disguised form of the complex conjugate of this product over here. And so when we add a complex number with its conjugate, we get twice the real part of that complex number. Hence, we get that twice the real part of the product of a with the complex conjugate of b is less than twice the modulus of a times the modulus of b. And so I canceled out the 2's over here. And one thing to note is that the modulus of b is actually equal to the modulus of the complex conjugate of b. And the reason for this can be explained in this formula over here. If we have, instead of a, we have its conjugate, well, we still get this expression over here. And now one property about the modulus is that the modulus of a product is the product of the modulus of the two terms. And ultimately, we get that the real part of the product of a times the conjugate of b is less than the modulus of that product. And now you may not have realized it, but we actually have proven the triangle inequality. And why is that? Because this inequality is always true. When we take the modulus of a complex number, it will always be greater than its real part. Because remember that the modulus squared is given by this expression. And so from this equality, we can see that the modulus of a complex number will always be greater than its real part. And since this is true, well, since we have worked with equivalence relations, we get that this inequality is also true. And so to summarize, the way we have proved the triangle inequality is by first assuming that it is true, and then working with equivalence relations. Furthermore, we have used the following properties over here. Most notably, the fact that the modulus squared is the product of the complex number times its conjugate. And also that when we add two numbers that are conjugate of each other, we get twice the real part of that number. And eventually, this led us to a result that is always true. And therefore, this proves the triangle inequality.